Hello, I'm Kylie Park, and I'm a junior at Lehigh University working in the Macintosh lab under Boyan Kim in the Chemical and Biomolecular Engineering Department. Our research, titled Novel Approach to the Synthesis of Gold-Supported Nanoparticles for HMF Oxidation, addresses climate change by targeting the plastics industry. The prevalent use of fossil fuel-derived polyethylene terephthalate, PET, exacerbates environmental issues, and we seek sustainable alternatives to mitigate this impact. Polyethylene furanate, or PEF, stands out as an alternative to PET, not only offering superior performance but also reducing non-renewable energy use and greenhouse gas emissions by 10%. The accompanying graph vividly demonstrates the significant environmental impacts of PEF over PET. Our research contributes to this transition by enhancing the production of FDCA, the building block of PEF. FDCA is synthesized from HMF oxidation, and we focus on gold as a catalyst for this reaction due to its efficient and stable nature. We specifically chose gold as a catalyst based on a unique observation from a cyclic voltammetry, or CV scan, of gold on carbon nanoparticles coated on fluorine tin oxide glass in 1 molar sodium hydroxide with 20 millimolar HMF as shown in Figure 5a. A unique peak, circled in red, was observed during the reverse sweep of the CV, which suggests that there is a specific interaction between the gold surface and HMF that is only evident when the potential is reduced. This could indicate that there is some synergistic relationship between the reduction of the oxidized species on the gold surface and HMF oxidation. We wanted to see if the same phenomenon would occur for bulk gold, which is why we examined gold wire in the rest of the figures here from 5b to f. Figure 5b is gold wire in 2 molar sodium hydroxide solution. The absence of the significant peaks in the reverse sweep indicates there is no specific oxidation process occurring, and if it is, it's not as evident without the presence of HMF. In Figure 5c, we see a CV scan of gold wire in sodium hydroxide solution with HMF. The peak around 1.1 volts in the reverse sweep suggests the occurrence of likely the same electrochemical process found in Figure 5a, where the reduction of the oxidized gold formed during the forward sweep. Figure 5d is a CV scan of gold with HMF below the potential range for gold oxide formation. The absence of the reverse peak confirms that the figure in 5c is related to the reduction of the oxidized gold species. Leveraging the strong interaction between reduced gold oxide and HMF oxidation, we modified the electrode to enhance and stabilize its catalytic activity. And so we developed a simple synthesis method that consists of 2 steps: gold oxidation and gold nanoparticle synthesis. For both setups, our mercury-mercuric oxide reference electrode, platinum wire counter electrode, and gold wire working electrode were used and run under counter-amperometry, 2.4 volts versus RHE for 10 minutes. The first step of gold oxidation was conducted in 2 molar potassium hydroxide solution and resulted in a reddish-brown color change. The second step, gold nanoparticle synthesis in 2 molar potassium hydroxide with 20 millimolar HMF, turns this oxidized gold wire black immediately, and we identify this black layer as AUX. This layer was made sure to be uniformly distributed, so 5 CV cycles were run at a scan rate of 10 millivolts per second over a range of 0.4 to 1.4 volts versus RHE. Scanning electron microscopy, SEM, and high-resolution transmission electron microscopy, HRTEM, were used to examine the morphology of the gold wires from steps 1 and 2 of the synthesis method. Figure 4a and b show the final results of steps 1 and 2 respectively. The CV for the oxidized gold wire resulted in uniform distribution of AUX particles. Figure 4c shows the oxidized wire when the first blackened layer instantly formed after being exposed to potassium hydroxide with HMF, and a much less uniform, rough, and porous structure can be observed. Figure 4d and e are closer images using HRTEM of the gold nanoparticles, which are the black circles, and the surrounding border, which is the film or layer X, which is not yet identified. By testing this AUX electrode and CV scans in potassium hydroxide with HMF, there is significant enhancement in electrocatalytic activity, as seen by the increased current density compared to regular gold wire in figures 5e and f, for both HMF oxidation and ethanol oxidation respectively. This confirms our hypothesis that electrochemically treated gold, AUX, with its increased active surface area, enhances current density and serves as a superior catalyst for HMF oxidation. In conclusion, a simple and easy synthesis method was established and showed promising results of enhanced HMF oxidation activity, which was also showcased in similar processes like ethanol oxidation. Our next step is to further investigate what the gold nanoparticles are supported on, X, and the underlying mechanism of the synergy between the AUX catalyst and HMF oxidation activity by conducting more spectroscopy experiments and electrochemical analysis. Thank you.